Bismillah ar-Rahman ar-Rahim. Today we will start with the Chapter 5, Modeling Harmonic Source. Traditionally, harmonic sources were represented by current injection source. So any harmonic can be represented by a current source. And the value of the injected current should be determined by the measurement, if it can be done. In the absence of the measurement, it is common to assume that the harmonic current is inversely proportional to the harmonic order. Okay, for example, over here we have the single line diagram of a generator feeding a non-linear load. So as a result, the non-linear load is represented by a current source, and this is the impedance of the transmission line, the impedance of the power source of the source. Those are the typical values for the harmonic value for different harmonic order. So if we have 6 pulse variable speed drive, we have the 5th and the 7th harmonic and the 11th harmonic, okay, 13th harmonic. But if we have BWM, we have also the same thing, right? But the percentage of those harmonic is higher. If we have arc lighting, we can have also the 3rd harmonic or triplet harmonic. We can have as well the 9th harmonic. But if we have switch mode power supply, all harmonic will present. All odd harmonic will be available. Now, how can we model the harmonic, or how can we do the harmonic analysis? Let us look at this example. So over here we have a power source, and then we have a transformer. Then we have on bus B we have a rectifier, which is a source of harmonic, and we have also capacitor bank. Okay, so this is the equivalent network. At the fundamental frequency, we have the source, the source impedance, the transformer impedance, and then we have the non-linear load, and we have the capacitor bank connected over here. Now, if we like to draw the equivalent network for the harmonic frequency, so the non-linear load will be represented by a harmonic source over there, and you will notice that the source, the voltage source, will be taken out because this voltage source is coming from a 3-phase generator, which will work only at let us say at 50 or at 60 hertz. So that's why the voltage source of the generator or the generator will not be present, will be short-circuited when we draw the harmonic equivalent circuit. Okay. Yes, so we have the harmonic source due to the non-linear load, capacitor bank, and then we have the equivalent impedance for both the source impedance and the transformer impedance. And then we can calculate the voltage at this bus by multiplying the current, of course, times the total impedance. And the total impedance in this case will be the impedance of the capacitor bank and this impedance that represent both the source and the transformer. Let us look at this example over here. So what we have over here, we have a voltage source, then we have a transformer that will step down the voltage from 154 to 34.5 kilovolt. Then we have the non-linear load rectifier, and we have normal load, and we have capacitor bank. So now let us look at those parameters or at those values that are given for those different sources, transformer and load. Okay, so he said that we have star connected inductive load that take 12 with angle minus 20 of current. So this load will take this current 20 with angle minus 20. Okay, so that will be the current taken by this load. Okay, and a star connected capacitance of 0.2 microfarad. So the value of this capacitor is 0.25 microfarad. And the 34.5 bus are fed from this transformer, and this transformer has size of 25 megavolt ampere, 25 megavolt ampere, and having an equivalent impedance of 0.01 plus J0.04. So Z for the transformer is equal to 0.01 plus J0.04 per unit. The short circuit impedance of the 154 kilovolt is 0.002 plus 0.006. So over here, the source impedance will be given by 0.02 plus 0.06 per unit. Okay, and what is the question? The question is, he said, sketch the diagram of the system and determine the harmonic current and voltage up to 47th order. Determine the total harmonic distortion for both the voltage and for the current. Okay, so this is the value of the harmonic current at fundamental frequency 8, at fifth harmonic 1.5, and so on. So the current will be given. So anyhow, what we like to do, we like to find the voltage, the total harmonic distortion for the bus voltage and for the branch current. Okay, so all those current need to be calculated. Okay, of course this is given. Now if I try to draw the network for the harmonic, then of course the harmonic will be provided the current to all this load. Okay, so anyhow we like to find the current in all those. Okay, so if I try to draw the network for the harmonic, so I have over here capacitor bank, I have over here also a load. Okay, I have over here the harmonic current. I have over here the impedance of the transformer. Okay, so this is bus B, and over here I have bus A, and then I have the impedance of the source. Okay, so this is the impedance of the source. So this is my source impedance, this is my transformer impedance. So again we need we need to find the current over there in the capacitor bank, in this load, and in this branch as well. We'll call it I source. So we need to find all those current. We need to find also the voltage over there and the voltage also at point A. So this is what we need to calculate. can we start with the calculation of the impedance of the capacitor bank? So we know that XC will be equal to 1 over J omega C. Okay, and the frequency is given as 50 Hertz, so we can find XC. Of course, then XC at any harmonic will be XC divided by H. Okay, so this is done. Okay, over here we have a load that take a current of 12 with angle of minus 20. So now if we like to calculate what will be Z load, will be the current, will be the voltage divided by the current, right? So V over the voltage over here at the fundamental frequency will be 34.5. So divide that one by the current, that will give us the load impedance over here, Z load. Okay, so this one will be, we can call it Z load. So that will give us Z load at the at the fundamental frequency. Okay, so this one will be Z load at fundamental frequency. Then we can find Z load at other harmonic. Of course, that will be R plus JXL time H. Okay, so Z total is given in per unit. Of course, we need to convert that one. We need to convert this one to ohm. Then we need to find the base value. Same thing. This is given per unit. We need to convert it to ohm. So we need to find also the base value. So let us move step by step as it is given for us over here. So the base impedance at the low voltage size with the transformer will be equal to V square divided by S, where S will be the base, will be the we can choose S base, which is the size of the transformer, 25, and the line voltage, of course, on the low voltage side will be 34.5. So that will give us the Z base. We are given the per unit impedance of the transformer, where the transformer, we are given the per unit impedance. So we multiply it by the base, and that will give us the transformer impedance in ohm. Of course, this one will be on the low voltage side. Okay. Now, if we like to calculate also the source impedance on the low voltage side, so what we need to do? So we know the now we choose the base impedance, okay, which is 47.6. So we can multiply the base impedance time the per unit, so that will give us the source impedance on the low voltage side. Okay, and that will be this value. Okay, if we like to find the source impedance at any harmonic, so of course R will be the same, and since over here we have XL, so I guess we need to multiply it by H. Same thing will be for the transformer, R plus, and for XL will be multiplied by H. The current of the load is 12. If we like to find what will be the load impedance, so it will be the voltage, which is 34.5 kilovolt, divided by root 3 to find the phase voltage over the current. That will give us the load impedance. And again, if we like to find the load impedance at any harmonic, this one will be multiplied by H. So capacitor bank, again, it's 1 over J omega C. So that will give us the value of the so that will give us minus J 12732.4 ohm. And again, if we like to find it at any harmonic, then we divide that one by H, because omega will be on the denominator. Okay, so that will give us the different impedance for the network. Okay, again, this is the network at the fundamental frequency with the existing of the generator, but when we try to draw the network for the harmonic frequency, of course, since this is only working at fundamental frequency, so it can be shorted out. So we have ZC, we have Z load, we have the source, we have the harmonic source, then we have the impedance of the transformer, the impedance of the source, this current equal to IC, this one I load, this one will be I source. Okay. Now, if we like to find the voltage and the different current at the fundamental frequency, because he told us that calculate all those, calculate the different bus voltage and different branch current at all those frequency, including the fundamental. So this is the circuit for the fundamental frequency. So the circuit for the fundamental frequency is given. Then if we like to calculate the IC, it will be the voltage divided ZC. I load is given. Okay, then IR, the current which is taken by the by this nonlinear load is also given, which is 8. Which is 8. Okay, so that current is also given. Okay, and then we'll able to find the different current in the system. Then I source, of course, looking at the circuit, I source will be the summation of IC plus IL plus IR. Okay, so that will give us the source current, and then if we like to find, we like to calculate also the voltage at each node. Of course, VB is already given. VA, it can be calculated, so we can calculate VA as the voltage at node B plus the voltage drop across the transformer. So VB, which is the phase voltage, plus the voltage drop across the transformer, which is IS times ZT. So that will give us the voltage of at point A or at node A. This is the phase voltage. If you like to calculate, the line voltage multiplied by root 3. But of course, this is at low voltage side. Okay, this is VA referred to the low voltage side. If it is referred to the high voltage side, we multiply it by the high voltage over the low voltage, just to find the source voltage on the high voltage side. So it becomes 154.1. Now we need to do the same thing. We need to do the same calculation, but now at the using the harmonic frequency. Okay, so we need again to find ICN, ILN. This is given, of course, and ISN. But now at the harmonic frequency. So we're going to start with the fifth harmonic. So if we have fifth harmonic, of course, what will be our circuit? If you remember from the circuit, so what we have over here, we have current source, load impedance, capacitor bank, and then we have over here the transformer and the source impedance are connected in series. Okay, so again, if we can just recall what we have from the harmonic frequency. So over here we have the load impedance, we have the capacitor bank over here, and then over there we have the transformer, and we have the source impedance. So this is what we have, right? This is what we have. Now the source and the transformer can be called Z3. So it will be the transformer plus the source impedance. Okay, so it will be Z3, and now it is we are looking at the, let us say, at fifth harmonic, so H will be 5. Now Z2 will be the load impedance at fundamental frequency, but now it will be at fifth harmonics, so it now will be 5. And Z1, so this is Z2, so Z1 will be the impedance by the capacitor bank, so it will be over H, because now we are looking at the fifth harmonic. So this is with regard to the different impedance, and of course all those three impedance will be connected in parallel. So to find the voltage at this node or at this node for the fifth harmonic, so what we need to do, we need to calculate the total impedance, you multiply it by the harmonic current. Right, so it will be the total impedance Z1, Z2, Z3 connected in parallel. Okay, so that will be Z total. So that will give us the total impedance. Then what will be the voltage at this node? Will be the total impedance times the harmonic current. Okay, so total impedance times the harmonic current, that will be the voltage at this node. Then now if we like to find this current, it will be the voltage, which is IR times ZT divided by this impedance. If Z1 represents the capacitor impedance, okay, at fifth harmonic, okay. IL, same thing, divided by Z2, IS, same thing, divided by Z3, okay. So that will give us the different current in each branch. Okay, so those will be the value. Okay, and again, if we like to find what will be the voltage at this node, so again we can say it will be either those impedance in parallel times the total current, or it can be, for example, IC times Z1 or IL times Z2 or IS times Z3. Okay, and this is what we did over here, and the value will be 16.5 volt. Now if we like to find the voltage source, so don't forget that, okay, this one will be the source voltage over there. So what will be the source voltage? So it can be the source current, because this is the source current at the fifth harmonic. So it will be the source current times the impedance of the source, right? So IS times Z source, that will be the voltage of the source. So voltage of the source will be I source times Z source. If we like to find only the magnitude, so it will be I source times the magnitude of the impedance. And if we like to find the line voltage, √3. And if we like to refer to the high voltage side, so the high over the low, okay? So that will be the value of the source, the voltage of the source, the line voltage of the source will have a value of 16.6 at fifth harmonic. Of course, we have to do the same thing at the rest of the harmonic, okay? So at the so we need to do the same calculation at 7th, 11th, 13th, and so on. And if we do the calculation, this is what we will obtain. So at fundamental, this is the current taken by the nonlinear load, the load current, source current, the current in the capacitor bank, the voltage at node B, and the voltage source at fifth harmonic, and so on until the 47th. If we like to find the total harmonic distortion, because we know that we have to take the square root of those divided by the fundamental, okay, and the square root. Okay, so that's all for this example. Now let us look at example number 2. It says that a converter drives a quasi-square current of 10 ampere peak value. So we have a current quasi-square. Okay, so this one will be the current against the time. Okay, so the value of the current will be 10 ampere peak. Okay. Okay, from a three-phase 11 kilovolt bus bar feeder to a factory, the load is a star-connected inductive load with RL and with LL. Okay, so actually we have almost the same as the previous system. Okay, so what we have over here, we have again a transformer. We have over here non-linear load. Okay, that will take 10 ampere peak, and it has quasi-square waveform. The voltage over here will be 11 kilovolt. The load is a star-connected inductive load, so over here also we have inductive load, star-connected inductive load. Okay, so we have R plus J omega L, and we have also capacitor bank. The value of C 1.7 microfarad, 1.75 microfarad. Put it from transformer, and the transformer is will step down the voltage from 132 kV to 11 kV, and the size of the transformer is 800. So S of the transformer is 800 kilovolt ampere. Okay, having equivalent impedance, and the transformer is having also equivalent per unit impedance, and the short circuit impedance of 132 system. So we have the source impedance. So over here we have also a source impedance, and then we have our generator. So this one will be Z source. So that will be the equivalent circuit. So it is almost the same as the previous problem. And now over here, say that sketch the diagram of the system and determine the harmonic current and voltage up to 23rd harmonic. Okay. So we need. Okay. So first of all, we need to. First of all, we need to determine the those harmonic. So we have a current waveform, which look like the square wave. So we need to do a Fourier analysis for the current waveform using Fourier analysis. Of course, if you look at this waveform, it is odd waveform. That means it has only B in component, and since it has also the what we call it that one, and that one, this pulse and this pulse will be opposite to each other. Okay, that means will not have any even harmonic. So let us try to do the analysis for the for the harmonics. Okay, so this one will be the current waveform. Okay, so we have one pulse, and then space we have another pulse. So of course it is an odd function. Then all AN will be 0. All AN component will be 0, and since it is half wave symmetric function, half wave, that means the pulse, the positive pulse and negative pulse actually will be opposite to each other. So that means there will be no even harmonic. So the harmonic will be 0 because it has half wave symmetric function. Okay, so AN will be 0. We left only with the BN, and BN only we're gonna have the odd component. So we take the equation of the current will be only constant I multiplied by sine, and we take the integration for the half period. Okay, so from 0 to t over 2, and then of course multiply it by 2, and then initially over here we have 2 over t. Okay, so that will be the equation. Once we take the integration, this one will be the final result. So Bn will be equal to that value. So Bn will be equal to 4i over n by cosine n by over 6. So at n equal to 1, this one will be, we're going to have this value at n equal to 2. At n equal to 2, of course, the odd harmonic will be 0, as we said. The even harmonic will be 0. It seems that also the treble harmonic will be 0 as well. Okay, so over here, if we put n equal to if we put n equal to 3, so that means supposed to give us also a 0 value, right? Because it will be pi over 2, so pi over 2 cosine pi over 2 will be 0. So that will be the Fourier series. Okay. Therefore, if we like to find the magnitude of the waveform, so this one will be the magnitude of the waveform, 4 root 3 over n by 2, so that will be the magnitude. Okay, and then it can be written as 7.8 divided by n. Now at the fundamental frequency, so n equal to 1, it will be 7.8 and so on. So those are the harmonic current that will be injected in the system, and he told us that we have to utilize harmonics up to 23rd. So this is what we have. And now I guess we need to repeat the problem again, the problem that we have already did in example number 1. So this one will be our circuit. Okay, so we have a capacitor bank, we have a load impedance, and we have the transformer and the source and the impedance of the source. And again, we will work on the low voltage side, so we need to find the base impedance on the low voltage side. So that will be the base impedance, so multiply the per unit by base, that will give us the impedance of the transformer. And same thing will be for the source impedance, we multiply it by the base, so that will give us the source impedance on the low voltage side. We find also the impedance of the capacitor, and then of course for any harmonic, so we can call it H, or we can call it N. So this one will be the impedance at any harmonic for the transformer, for the system, for the load, and for the capacitor bank. Okay. Now if we like to find again the voltage at this node, so what we need to do, those are connected in parallel. We multiply that one by the source by the fifth harmonic, and that will give us the voltage at this node for the fifth harmonic. If we like to find the current, then voltage divided by Z1, the current over there, voltage divided by Z2, and so on. Okay. And then again, we're going to find V source, and then we're going to refer it to the high voltage side. So this one will be V source for the fifth harmonic. Okay, so that will be for the fifth harmonic. This one will be our final result. So for the fifth harmonic, the current that passes through the capacitor bank, the current that passes through the load, a current that passes through both the transformer and source impedance, the voltage at node B, and the source voltage. And then we can do it for the rest of the harmonic. By the way, we can model the system by using MATLAB, so it will be very easy. So again, we have the 5th harmonic, the 7th up to the 23rd harmonic, and then we have so those harmonic current will feed our system, which consists of capacitor bank, load impedance, transformer impedance, and the source impedance. So if we do this one in MATLAB and we do fast Fourier transform, we're going to get exactly the same value. For example, if we look at the 5th harmonic, that will be the value of the 5th harmonic if we are looking at the capacitor current. So over here, say that for the capacitor current, the capacitor current at 5th harmonic will be equal to 0.27. This is from MATLAB, and if we look at our analytical result, we have exactly the same value, 0.27. Okay, and of course we can do the same thing with the other. Okay, so that's all for this unit or for this chapter. Thank you.